Swayam Prabha. Digital India. Educated India.
Hello and welcome back everyone. We are learning the basics of building construction and currently we are learning the module on PCC and RCC. So in the last lecture we were having an introduction on PCC and today we are going to take this discussion forward and then also learn a little bit about RCC. So first let's learn about the properties and tests for concrete. Now when we are looking at the properties of concrete, we mainly look at the strength, the durability, the workability and the economy. Now these four factors combined together will ensure that our concrete is the right choice for a particular application. For the purpose of measuring the strength, we do the cube test. To check for the durability of concrete, we see the water absorption test, the water permeability test and rapid chlorine penetration test. With respect to workability, that is how easily we can work the concrete in a certain shape or mixture, we do the slump test, the compacting factor test, the VB test and vibro workability test. Let's study a little bit further in detail into these aspects. So when we talk about strength of concrete, it is this ability to resist force that is known as the strength of concrete. Now strength of concrete can be defined as the unit force required to cause rupture in the concrete form. Now IS code 516, it defines the requirements related to strength of concrete for different construction types. And the test, as already mentioned, is cube test. When we talk about durability, it's the property of concrete by which it is capable of disintegration and decay. It may be caused due to atmospheric changes, moisture changes, temperature variations, etc. So this is tested by the water absorption test, water permeability test, rapid chlorine penetration test. So this tells us how quickly the concrete actually disintegrates and decays. So accordingly we know what is the durability that is expected of the concrete that we have produced. Then comes workability. Now workability of concrete is probably the most important property and it is defined as the ease with which we can mix, handle, transport the concrete. We can easily place and compact the concrete. So basically dealing with the concrete and mixing or shaping it the way we like. So that essentially is going to define how easily we can apply this concrete to various uses in our construction. So workability forms probably one of the most integral parameters when choosing the right mix for our concrete. Now IS code says the specifications of workability of concrete and we can test this by the slump test, which is actually shown here with the help of this figure. We can see that the slump test is essentially putting this concrete in a certain shape or mold. When removing the mold, how much it slumps or kind of droops, that will define the workability of our concrete. So that is the slump test. Other than this, we can also have the compacting factor test, the VB test and the vibro workability test. Now economy is also an important parameter because the cost of the raw materials, production, processing of the concrete, curing of the concrete, all this will incur some specific costs. Now this will depend upon, of course, the type of concrete we are going for, the grade of the mixture. So we have to ensure that we can get maximum strength, durability, workability from our concrete while restricting the cost as much as possible. Of course, the cost of each of the individual constituents, for example the cement, the aggregates, etc., that we are trying to put together to form the concrete, that will vary depending upon its quality, depending upon its application that we are going to put it to. So in totality we want to ensure that whatever purpose we are going for, the concrete mix that we are generating should be able to provide us the best characteristics with the least amount of expenditure. Now there are various methods of proportioning the concrete mixes. It is very important that we proportion our concrete mixes. I'm sure we've all learnt about, 1:2, 3:2, something which is basically proportioning our concrete into its constituent parts. Now every application has a different proportion. IS codes tells us what is the right proportion in which we can take a certain concrete mix for different applications. Like if we are doing it for PCC, for RCC in different parts of the building components, the mixture will be varying. But when we are doing this proportioning, we have to follow certain methods to ensure that we are getting the right mix or ratio. So the first method is arbitrary method. This is adopted for works which are of small magnitude and are moderate importance. So it is not at a place where we are making something very structurally important or where the integrity of the entire structure depends on this mix. It is for small jobs. So for that, arbitrarily we can take the different constituents and mix them together in a certain ratio which visibly looks okay. The next method that we can use for proportioning is called the minimum voids method. Now the voids of the coarse aggregate and fine aggregate are determined separately to keep the voids in this concrete mix to the minimum. The maximum density method is similar to the minimum void method. It was later improvised by Fuller, and he did this to formulate the grading of the materials to achieve maximum density to the concrete mixes. So here we are not just trying to control the amount of voids like in the previous method. Here we are trying to achieve the maximum density in the concrete mix when we are bringing together all the constituents. The next method is the fineness modulus and the water cement ratio method. Here we are taking the fineness modulus results and the Abraham's water cement ratio law to actually determine that we are getting the right mix for our concrete. So basically in a concrete mixing, we are going to have the cement paste, that is the cement and the water mixed together, the aggregates in a certain proportion, and air voids. Now let's talk about grading of concrete. What do we mean by grade of a concrete? Now grading of concrete in India is done as per the IS code 456/2000. Concrete has been designated into 7 grades, with each grade defining a standard compressive strength of concrete measured in Newton per millimeter square. Now concrete grades below M20 should not be used for RCC works. Above that we can go up and use it for RCC works based on the application or part of the building component that we are using it for, but anything less than M20 is not suitable for application in reinforced concrete works. So in totality we can grade the concrete into various subcategories based on the compressive strength. So the specific characteristic compressive strength of 150 mm cube at 28 days is measured in Newton per millimeter square, and according to that we are subcategorizing it into different grades. Now with respect to ordinary cement, M10 actually refers to 10 Newton per millimeter square compressive strength. Now this compressive strength, again reminding you, we are applying this on 150 mm cube at 28 days. So the curing process is over, and then the Newton per millimeter square compressive strength we are measuring. So if it is coming at 10, then it is an M10. If it is 15, it will be M15. If it is 20, it is M20. So based on this result, we are grading it into a certain type of concrete. So ordinary concrete will be M10, 15, 20. If we go up to 25, 30, 35, 40, M45, 50 or 55, these are standard concrete. We can use this even for application in RCC works. We can go up to M80 if we are dealing with high strength concrete. So M60 to M80, it could be used for high strength concrete applications. There are certain permissible stresses in concrete which are also defined by the IS code 456/2000. So the permissible stresses in bending compression and direct compression for various grades of concrete are specified. So if we see this list of M10 to M50, we can see here that the bending permissible stress in compression and direct ones are defined. So as we move down this list, that is we are moving towards M50, you will see that the permissible stress in compression for bending, for direct compression, both are increasing, gradually increasing. Let's talk a little bit about the nominal and design mix of concrete. Now, in nominal mixed concrete, it may be used for concrete grades M5, M7.5, M10, M15 and M20. So, what we are doing is, when we are proportioning the nominal mixed concrete, we are taking the total quantity of dry aggregate by mass per 50 kg of cement to be taken as the sum of the individual masses of fine and coarse aggregates put together, and the maximum amount of this mixture of dry aggregates that we can take in mass per 50 kg of cement. That is defined. If we are dealing with M5, that can be maximum 800, and as we move down the list towards M20, it will reduce. So, in M20 we can have about 250 as opposed to when compared to the 50 kg of cement that is being mixed with. So, that means as we go down the list, that is, a compressive strength is increasing, we are reducing the amount of dry aggregates that we are proportionately mixing with our cement of the same quantity. Now, when we are proportioning a fine aggregate to coarse aggregate, because of course in this mixture of dry aggregates there is also a proportion of fine versus coarse aggregate. Now, generally a ratio of 1:2 is taken. The upper limit is 1:1.5 and the lower limit of 1:2.5 mix we can take when we are comparing fine aggregate to coarse aggregate by mass in this mixture of total dry aggregates that we are taking. Of course, the quantity of water is also very important. As we learnt in the previous lecture, water cement ratio will determine my ultimate strength of the concrete mix. The more amount of water I keep adding to this mixture, first of all, beyond a certain limit, the cement is actually not getting hydrated by the water. It only requires probably 0.5 portion of that water. So, that nominal mixture of water has to be provided. Anything above that for workability that we are adding, it is going to contribute to reducing the strength of that concrete. But nonetheless, there is a proportion which is specified by the IS code at which the water is added to this mixture. So, if we are adding water, we measure it in liters, maximum liters that is permissible with respect to 50 kg of cement. So, if you are dealing with lower grades of concrete, that is M5, that could be 60 liters. If we are going up to M20, then that would be 30 liters. So, the amount of water we are reducing, because the relationship is inversely proportional. If we want to increase the compressive strength that our concrete is able to deal with, we are going to have to reduce the amount of water we are adding. Now, when we are talking about reduction of the water, it of course cannot be too low. The water cannot be so low that the minimum hydration of the cement has also not happened. So, the lower limit is also set. Now, IS code is providing us the sufficient quantity of water which is just right for this particular mix. This will allow us to mix the aggregates, the cement and the water in the right proportion to arrive at the specific grade of concrete that we are aiming for. Design mixed concrete is designed to produce the grades of concrete having required workability and a characteristic strength which is not less than the appropriate values as defined by the IS code. We can also go for certain situations where, based on the application that we are using or the part of the building component that we are dealing with, we might go for the proportion which is just right for us. But even then, the permissible limits are set by the IS code. We cannot go beyond that. Now, let us take a look at how we go about doing concrete works. Now, when we are preparing and laying concrete, there are certain steps we will have to follow. Now, these are usually put together in 6 main stages. So, B is batching of materials, M is mixing of concrete, T is the transportation of concrete, P is the placement of concrete at required location, then comes C, compacting of concrete, and C, curing of concrete. So, batching, mixing, transporting, placement, then compacting and curing of concrete at the location. So, these are the 6 steps that we are going to have to follow in any concrete work. Now, what does each of this step actually mean? Let us see. First, B for batching of materials. In order to ensure that the quality of concrete is maintained, it is necessary that all the materials are measured accurately within the permissible tolerances. We were just talking about the proportions. So everything has to be in the right quantity and has to be mixed in the right way. So first of all, batching of materials can be done manually or it can be done using a batching plant. Now batching depends on the magnitude of concreting work involved and the rate at which the concrete is required to be produced. Now if we are dealing with a small quantity and we are doing a small construction work, in that case we can do it manually. We can manually mix the different proportions together. But if we are dealing with a concrete work which requires much larger quantity of concrete, and not just that, we also need it at a fast rate. That is, we constantly need to supply the concrete for a major work. In that case, it's very difficult for us to keep manually doing it at the right proportion. We are bound to make certain mistakes. So in that case, we might want to go for a batching plant. Now the batching of different materials is done such that the cement is measured by weight. Here we generally take bags of cement, each bag having 50 kgs. Then we take the fine aggregates. Manual batching on site is done. We can use a sieve to be able to segregate the right size of the particle, and coarse aggregate is done through mechanical batching because it ensures it is larger size of particles. They are oftentimes angular in shape. Manually sieving through them is quite difficult and might lead to certain injuries on site. So we might want to go for mechanical batching of this because of its shape and size and also the weight of this material. Coarse aggregates are definitely going to be heavier than the fine aggregate that we are dealing with. So sieving them manually will be a very tiresome task, especially if we are going to create a larger quantity of concrete at the site. The next stage is called mixing of concrete. Now the operation of manufacture of concrete is known as mixing. Now mixing can be done again by two methods. The first is hand mixing. This is done manually on a steel plate. The size of the steel plate is kept to about 2 meters cross 2 meters, and a hard clean surface is ensured on which the mixing is to be done. Now this method is resorted when the quantity of concrete needed is very small. This we can do manually. Now sand and cement are first mixed in the dry state. Now this is followed by the addition of coarse aggregate. So we are taking the fine aggregate and the cement, we are first mixing them up in the right proportion. Once that is thoroughly mixed, we are adding the coarse aggregate to it. The mixture, when well mixed, is added with water at predetermined amount to form the concrete. So first fine and aggregate and cement together in dry state, then add coarse aggregate still in dry state, then we add water to it in the right proportion to get the concrete form. In case of the second process, which is machine mixing, here we are using some mechanical mixer to mix the concrete. We are not doing it manually anymore. Now even in this case, we can have two types of machine mixing. One is we can have a batch mixer that is used for relatively smaller works, and there is another option of using continuous mixtures. This is used when mass concreting has to be done. We are dealing with a very large project where there is a continuous supply of concrete which is necessary. So this continuous flow of concrete is ensured by using a continuous mixture. So usually in this, the concrete and the cement and the other components are being added continuously, and the machine is churning out a constant flow which is then diverted to a certain direction where the batching and mixing is done, and then it is diverted into a certain direction for placement. The next stage is called transportation of concrete. Now here the handling of concrete from the place of mixing to the place of final deposit has to be done. Now if segregation occurs during transport, concrete should be remixed before placing. Now if it is at a place where we are actually using humans and they are transporting this in pieces, so probably they can take containers or truffles to actually transport it from one place to another. Other than that, we can also have the machines. If we are doing mechanical mixing, it is possible to directly divert it to the portion where we are going to place it. Now placement of concrete at a required location where it is to be placed and compacted, then the setting will commence. This should not be disturbed subsequently, and the concrete should be uniformly spread out on all sides to provide better compaction. Now, compacting of concrete is done to remove any entrapped air during the production of concrete and ensure that a uniform dense arrangement is reached in the end. Now, concrete should be thoroughly compacted during the operation of placing to achieve maximum strength and durability. Now, generally, to ensure that we can do the compacting well, we use vibrators. So, it's almost like when we are trying to pour, let's say, certain particles inside a container, oftentimes we see that if we vibrate it, it sets well. So, all the air gaps which are there inside that material is removed and it sets to form a uniform finished surface on top. So, it's the same principle that we are applying here. So, we are vibrating it. So, if there is any entrapped air or if there are any gaps in the concrete, it will be removed and it will form a uniform dense arrangement. That will ensure that the ultimate, after setting of concrete, we are getting a durable surface. Now, the vibrators that we use for the purpose of compacting of concrete can be of various types. Now, it can be external, that is commonly used for thin sections. This is placed against the concrete framework and a vibrating force is conveyed for compaction. Now, internal vibrators, here these are commonly used for larger works for flat surfaces. It consists of a metal rod like vibrating head which is immersed in the full depth of concrete layer. It may be available in either fixed shaft driven type or motor head type. Surface vibrators are mounted on platforms and they are commonly used to compact and finish bridge floors, roof slabs, etc. Vibrating tables are used for consolidation of precast units. Then comes the curing of concrete. Now, this is the most essential operation in which the concrete is kept continuously damp for some days to enable gain of strength. Now, curing replenishes the loss of moisture due to atmospheric evaporation. The nominal period in between 7 to 28 days is spent on the process of curing. It depends upon the scope of work. Now, that was about the concrete and its grades and the process of actually creating it and setting it and then curing it. Now, let's talk about reinforcements, because to form R.C.C, reinforced cement concrete, in addition to the concrete component, we are going to have to add reinforcement to this entire arrangement. Now, the material which is selected for use in reinforcement should have the following characteristics. First of all, it should be able to develop perfect bond with concrete. It should have coefficient of thermal expansion similar to concrete, obviously because it's going to be integrated together. So, a part of R.C.C cannot have a different thermal expansion than the rest. It should definitely have very high tensile strength, which is exactly the reason why reinforcement is being added to this concrete, because concrete can have good compressive strength, but it is not going to be able to deal with tension. So, to be able to deal with tension, we are adding the reinforcement to this entire arrangement to form reinforced cement concrete. So, that means we have to use a material which has got high tensile strength. It should not produce any defect or any harmful effect when it comes in contact with the concrete or other materials. It should be easy to cut, bend, bind or weld, because it is possible that we are applying our R.C.C to different types of shapes. So, it should be able to accommodate that change in shape. It should also be easily available. So, we want to make it locally available, otherwise it would increase the cost of our overall construction. It would make it more convenient, delay construction process if it is not available everywhere. Now, if we see these criteria, these factors that we just enlisted, we will see that steel meets all of the above mentioned criteria and it can very much be used as a reinforcement without a doubt in our construction purposes. Now, steel reinforcement, when we use it for reinforced concrete works, we can use different types. Now, the specifications or characteristics of these reinforcements are specified in the IS codes. We can use mild steel bars, hot rolled mild steel deformed bars, medium tensile steel, hot rolled medium tensile steel deformed bars, hot rolled high yield strength deformed bars, cold worked steel high strength deformed bars. We can also have hard drawn steel wire fabric if you are dealing with thinner surfaces or surfaces which are to be shaped in a certain way. we can use this, we can use rolled steel as well. So there are different types and their specifications or characteristics, and the way they have to be worked with is specified in specific IS codes. So these are some examples of different types of reinforced bars. We can see different shapes are possible. Their surfaces for characteristics will be different, and each of these will find application in different places. There are certain permissible stresses in steel reinforcements. We were talking about permissible stresses in concrete. Steel would have certain specifications as well. So if we are dealing with mild steel bars, we'll see that in tension it should be able to accommodate 140 Newton per millimeter square, and if it is over 20 mm, then in that case those bars should be able to deal with 130 Newton per millimeter square. This is when we are dealing with mild steel bars. The compression in column bars should be also 130 Newton per millimeter square. If you are dealing with medium tensile steel, about 130 Newton per millimeter square is expected in the same categories. For high yield strength deformed bars, this would go up to about 230 Newton per millimeter square in tension, and in compression about 190 Newton per millimeter square. With respect to compression in bars in beam or slab, for mild steel bars or medium steel bars or high yield steel deformed bars, it is going to be such that the calculated compressive stress in the surrounding concrete is should be multiplied about by 1.5 times the modular ratio. If we are dealing with compression in bars in the beam or slab, it depends on which type of rod or bar we are dealing with. So this could range from 140 Newton per millimeter square to 190 Newton per millimeter square. So depending upon the type of bar that we have selected for our reinforced work, the permissible stresses will vary. So accordingly, based on the stresses we are expecting our structure to undergo, we can select the right kind of bar which is applicable to us. There are certain characteristic strength that steel reinforcement has. The characteristic strength of the steel reinforcement means that's the value of the strength of steel below which not more than 5% of the test results are expected to fall. Now the characteristic strength is taken as the minimum yield stress for the grade of steel used in the manufacture of reinforcement. Now here we are dealing with mild steel bars. Averagely the yield stress would be 250 Newton per millimeter square. For high yield strength deformed bars, this would go up to 415 Newton per millimeter square. For high yield strength deformed bars, this would further go up to 500 Newton per millimeter square when we are dealing with the yield stress. Now how do we go about handling reinforcement at the site? It is necessary to prepare a bar bending schedule for the structural drawing prior to the start of handling reinforcement at the site. Now bar bending schedule is a descriptive list containing details regarding the exact shape, dimension and diameter of each and every bar together with the number of bars for each shape. So it's basically creating a list. These are the types of bars needed, this is their shape, this is their dimension, this is what their diameter is, and this is their frequency, that is the number of each such said bars that we are going to use at the site. So together that forms a total list which becomes our standard go-to when we are doing the construction process. The bars are cut and bent as per these requirements, and it is important to check that the reinforcements are clean and free from any loose rust, oil or any other coating before we actually place it into the formwork. Now let's learn about reinforced cement concrete. The cement concrete undertakes the compression load in the R.C.C. but cannot take tensile strength. This results in cracking. Now the steel members take the tensile strength due to elasticity, but it is subjected to buckling due to slenderness. Therefore, the R.C.C. structures are created in a combination of steel and cement concrete, and that mixture, this compositely is known as reinforcement concrete or reinforced cement concrete. So we are mixing steel and cement concrete because of their inherent properties. When put together, they are able to deal with both compression and tension. The combination of steel and concrete becomes workable on account of three reasons. The concrete grips the surface of the steel bars very fast in the duration of the setting. Therefore, concrete can transmit the stresses to steel. The coefficient of linear expansion of concrete and steel is almost the same. Therefore, no internal stresses are created due to variations in temperature. Now, the coating of cement grout on the surface of the steel bar protects them from corrosion and does not produce any adverse chemical effects which may affect the structural stability of the building. There are several advantages of reinforced concrete. It is economical. The monolithic character provides more rigidity to the structure. It is durable and fire resistant. It does not decay and is not affected by insects. It is almost impenetrable to moisture. The cost of maintenance is also very low. Materials used in construction are easily available. The flexibility of reinforcement and the fluidity of the concrete allow the preparation of the reinforced members in any desired shape. So, if in our construction we have designed something which is oddly shaped, it is possible for us to use R.C.C to create it. Some basic assumptions are considered in the case of reinforced concrete for the design purposes. First of all, it is considered that a transverse section plane before bending remains plane after bending. The moduli of elasticity of steel and concrete are constant. All tensile stresses are taken up by the steel reinforcement only, and the resistance of concrete to tension is considered to be nil. The bond between concrete and steel is supposed to be sufficient to make them act jointly to resist tensile or compressive forces. There are several causes of failure of R.C.C. So, an R.C.C member may be expected to fail because of the following reasons. Now, when the member is subjected to excessive tension so as to exceed the permissible stress in steel. Now, when the loading is such that the compressive stress in concrete exceeds its safe permissible value, even then the R.C.C structure will fail. Now, when the concrete is subjected to excessive shear, on account of the slipping of steel bars from concrete, it can also fail. Due to bad quality of materials which are used, shrinkage, creep or thermal effects can be observed. And when the member is subjected to extremes of temperature, aggressive liquids or gases, in that case also R.C.C can fail. There are certain design requirements that have to be followed when building R.C.C structures. To decide the suitable arrangement of beams, columns, foundations, etc. for the structure on the layout plan, we have to ensure that we have a well thought out plan beforehand. Based on this, we know exactly the constituent parts, their shape, size, they are already cut to size, and all this arrangement has to be ensured depending upon whether we are dealing with beams or columns or foundation or lintel. Based on that, our design plan has to be, or layout has to be prepared beforehand. We have to determine all types of load and forces to which the structure is likely to be subjected during its entire lifetime. So, let's say we are dealing with a structure which is in an earthquake prone area, or it is going to be, it's a tall structure, it's going to be subjected to a lot of wind. So, these things will have to be considered beforehand when we are determining the amount of reinforcement that we have to provide, what is the grade of concrete we should use, what should be the size of our members. So, all this has to be thought of beforehand. So, even though an earthquake is not expected to happen every day, but the fact that it is possible because our structure is in a certain seismic zone, we have to take that into consideration, because during the lifetime of our building, it is possible our building will be subjected to that situation. So, our members should be designed in such a way that it takes into account that fact. So, seismic design philosophy of course is another aspect that needs to be studied in detail. You can of course study it separately to understand what I am talking about now. But all these types of loads, in addition to the dead and live loads and the self weight that our structure itself has, there are many other loads and forces the building will also be subjected to. So, everything has to be considered before we determine what type of constituent members we are going to use for our structural members. Now, to analyze the structure structure and calculate stresses, moments and shears etc. in the members, we actually have to do calculations to ensure that we know what is the stress, what moment, what shear is expected in each specific member, and whether the reinforcement and the concrete grade that we have selected is suitable for the same. To work out the safe sections and areas of steel for the different members, that is a design requirement that has to be taken care of. We have to provide the calculated area for tensile, compressive, shear or temperature reinforcement in the correct position to ensure that stresses remain within the permissible limits. Today we have talked about the permissible limits for both the concrete as well as the steel, which is a constituent part of the R.C.C. So this permissible limit should not be crossed, so that we have to make sure by doing ample amount of calculations beforehand. To provide sufficient anchorage for all reinforcement to meet the anchorage and bond requirements. So our IS code also specifies the anchorage and bond requirements. We have to ensure that the right ties at the right spacing center to center is used. That will also ensure that the overall integrity of the structural member is maintained. Now, while we are talking about cement concrete, we are talking about details of the reinforcement. We have already learned to make the cement concrete, how we are mixing cement aggregates, which includes fine and coarse aggregate, and water in the right proportion. We have learned about the chemical compositions, the tests to ensure the same. Then we looked at how we can bring all of these three components together and we can form R.C.C. One thing that we haven't discussed in detail in this lecture is the form work. That is, when we are creating the R.C.C. in a certain shape, we are putting it to a shape, we require form work to be able to do that. That is of course handled separately in a different module. So with that, we are coming towards the end of this particular module and lecture as well. Let's take a quick recap before we say goodbye for today. So first we started with learning about the different properties of concrete. So strength, durability, workability and economy are the primary factors that we will take into consideration. So strength can be measured by using the cube test, durability can be measured using the water absorption test, water permeability test and rapid chlorine penetration test. The workability can be measured using slump test, compacting factor test, VB test or vibro workability test. And we also need to ensure that we are reaching strength, durability, workability by keeping the cost to a minimum. So economy is the fourth factor of consideration. When we are preparing and laying concrete, we follow 6 steps: batching, mixing, transportation, placement, compacting and curing. Now each of these stages we've learned that in batching, mixing we can do it manually, we can do it mechanically as well. Even for transportation, it will depend upon whether we are creating small quantities of concrete or larger quantities, or whether we require constant flow of concrete for the process of placement. The compacting of concrete uses different types of vibrators. The curing of concrete will require a specific time depending upon the scope of work. These are some of the references that you can take a look at for further study. Thank you for tuning in today. We have just finished learning the module on PCC and R.C.C. In the previous lecture, we had talked about PCC, and in this lecture, we have dealt predominantly with R.C.C. Thank you so much. See you soon.